Principle of cross products is the tool that we use when we are trying to evaluate proportions or solve proportions for an unknown. So if we look at these proportions that we've been given, 3/5 equal to 2/7, we want to determine if that proportion is true. Is 3/5 in fact equal to 27/45? Not 2/7. So I'm going to use my cross products, multiplying 5 times 27 and 3 times 45. And since both of these equal 135, this proportion is true. Likewise, evaluating the cross products over here, I get 6 times 15 and 5 times 24. And since 6 times 15 is equal to 90, and 5 times 24 is equal to 120, because these cross products are not equal, this proportion is false. Now you already had a way of figuring out whether or not these were true using the math that you knew for fractions. Because I can take 3/5 and multiply it by a fancy version of the number 1, 9/9, to reach 27/45, I knew that 3/5 and 27/45 were equivalent fractions, and therefore this proportion was equal. Likewise, since in order to get 5/6 to equal 15/24, there is no version of 1 to multiply by, since 3 times 5 is what gives you 15, and when you multiply the bottom by 3, you do not get 24. I could have said that that one was false, just using what I knew about fractions. But when we get down to problems like 17 and 18, especially 18, where our numerators have little mini expressions of their own in them, you'll see how cross products can really come in handy. So using what we know about cross products, I'm going to set up an algebraic equation where I say that 14 times 7 needs to equal 49 times n, because I want this proportion to be true. Since 14 times 7 is 98, when I divide both sides by 49, I will get that 2 equals n. And if you substitute that value back in there, 14/49 does in fact equal 2/7, because 2 times 7 is what gives us 14, and 7 times 7 is what gives us 49. But let's look at how this same theory applies with one that has algebraic expressions in their numerators. I'm still going to be multiplying 4 times c minus 6, that's that cross product, and setting it equal to 8 times c plus 2. Then, just as I've solved all other algebraic equations, I'm going to use the distributive property first to distribute the 4 and the 8. Then move all of my variable terms to one side and all of my constant terms to the other side, leaving me with a negative 4c equaling, looks like positive 40. Then I'll divide by negative 4, and I get c equals negative 10. Now, guessing that negative 10 was the number that needed to go in there to make this an equal proportion, using what we used to know about fractions, would have been pretty tricky. So let's make sure that this answer actually works. When I replace the c's with negative 10, negative 10 minus 6 over 8 becomes a negative 16 over 8, which is negative 2. And negative 10 plus 2 over 4 becomes a negative 8 over 4, which is also negative 2. So it looks like negative 10 is our value that works for C.